So far, we've been talking about addition reactions that follow what's called Markovnikov's rule. So Markovnikov's rule, we would think about if we're adding Hz across an alkene. So Hz could be something like Hx, like HBr, HCl. Remember, X means halogen. Or it could be water. Or it could be an alcohol. So we've seen examples of all three of those. So with Markovnikov's rule, if you're adding Hz across your alkene, Markovnikov's rule tells us that the Z attaches to the more substituted alkene carbon. So that's going to give us a particular constitutional isomer product. Now, for some of these reactions, conditions exist that will give us the opposite result of Markovnikov's rule. And so we would call those anti-Markovnikov reactions or processes. So we're still adding Hz, but in an anti-Markovnikov reaction, the Z attaches to the less substituted alkene carbon. Okay, so let's look at some examples of what we've been doing. So we can make Markovnikov alcohols from alkenes. And when we use the term Markovnikov alcohol, that means that we're making an alcohol using a reaction that follows Markovnikov's rule. So we saw two ways to do this. Let's use this as our alkene. So what we know is that we can use a catalytic amount of a Bronsted acid in the presence of water. Now that catalytic acid, remember, is going to be one of these guys: nitric acid, sulfuric acid, or tosic acid. So those conditions will give us the Markovnikov alcohol. And while we don't see it in this particular structure, it can happen in others. Because the reaction goes through a carbocation intermediate, we have to be on the lookout for the potential for rearrangements. So that was one way that we could make a Markovnikov alcohol. Another way to make a Markovnikov alcohol that avoids the possibility of those rearrangements is oxymercuration-demercuration. So step 1, mercuric acid and water are used to treat the alkene, followed by step 2, which involves sodium borohydride. So that gives us the Markovnikov alcohol. So this is called oxymercuration-demercuration. And there are no rearrangements because this mechanism doesn't involve carbocations, as we saw previously. So those are Markovnikov alcohols. We can also make what's called an anti-Markovnikov alcohol. And so let's summarize that here, and then we're going to look at the details. So starting from an alkene, we'll just use the same example. What we want is the result where, yes, we're adding the elements of water across the alkene, but instead of having the OH group attached to the more substituted carbon, it attaches to the less substituted carbon. Okay, so these two components are new in the reaction. In order to do this, we're going to use a sequence called hydroboration oxidation. So this is hydroboration oxidation. And it too has no carbocations. Now this is all summarized in the box up at the top, but let's just write the reagents in as practice. In the first step, we're going to use a compound called borane. So we'll just say BH3. Now there's other things that we could use here. We'll talk about those a little bit. In the second step, we're going to treat this with basic aqueous hydrogen peroxide. That's the oxidation step. Okay, so that's a summary of how we can make alcohols from alkenes. We can either make Markovnikov alcohols or anti-Markovnikov alcohols. So now let's look into the details of how we'd make the anti-Markovnikov alcohol through hydroboration oxidation. Okay, so it's a two-step process, and the first step is hydroboration. So let's use this alkene, and we're going to treat this with BH3. And what's going to happen is that the BH3 is going to add across the alkene in this fashion, and that gives you what's called an alkyl borane. Okay, so BH3 itself is called borane. So let's talk a little bit about borane, because it turns out borane is a little bit problematic. So if you get two borane molecules together, they like to get together. And so they're going to hook up with each other. It probably didn't sound very good. They're going to bond to each other, and they're going to make this guy, B2H6. Okay, so the BH3 pieces are identical. We call those monomers. So each of these is a monomer. And when you hook two of them together, what you get, the B2H6, is called a dimer. Now, the dimer, B2H6, as it turns out, is toxic and flammable. So although we would be observing safety precautions and wearing safety goggles and lab coats and doing this in a fume hood, anytime we can avoid using toxic, flammable chemicals is a good thing. And so what happens is that people tie up the BH3 in a different form. So they're going to put it into a solvent. Now the solvent looks like this. The solvent is called THF, and that stands for tetrahydrofuran. So when you place BH3 or borane in THF, remember that the boron is sp2 hybridized. So it has an empty p orbital because it only has 3 bonds, the 3 bonds to those hydrogens. The empty p orbital makes it a Lewis acid. So BH3 is a Lewis acid by virtue of its empty p orbital. And that makes THF a Lewis base because it's donating a pair of electrons into the empty p orbital on the Lewis acid BH3. So remember, a Lewis base is an electron pair donor. A Lewis acid is an electron pair acceptor. So now these two get together. And so what that gets us is this guy. Which is called BH3 THF. So up above, where it says step 1 hydroboration. Over the arrow, I just wrote BH3. And you might see that written. You might also see B2H6, or you might see BH3THF, because that's commonly how it's stored and used. When a Lewis acid and a Lewis base get together, the product is called a Lewis adduct. So BH3THF is what's known as a Lewis adduct. Okay, so how does this happen in the first step? How does the alkene get hydroborated? Remember that the boron in BH3 is sp2 hybridized. It's forming 3 bonds, and so it's short an electron. It has an empty p orbital. So the alkene is going to use its pi electrons to attack the empty orbital in the boron. The hydrogen then gets transferred to the more substituted alkene carbon. So there's a couple of reasons, but one of the main reasons why we get the result that we do with the boron group attached to the less substituted alkene carbon is because that's a less sterically hindered carbon. Less sterically hindered means that there's more room around that carbon. If it had steric hindrance associated with it, that would mean that it had a lot of groups attached to it, and it would be hard for another reagent to approach that carbon. So in this case, one of the main reasons why we get the result that we do is because the BH2 group attaches to the less substituted alkene carbon, because that carbon is less sterically hindered. And by that, we mean that there's more room around it for the BH2 to attach. So because the BH2 is the bigger group, it's going to want to attach at the position where there's more room for it to attach. So steric hindrance, that's a new term for us, but it goes hand in hand with what we already saw when we talked about conformation. We talked about steric strain. So strain, steric strain, refers to something that's happening within the same molecule. So groups that are within the same molecule are getting too close. Steric hindrance comes up when you have two things that want to react with each other, but one of them is blocked because of the presence of a lot of bulky alkyl groups or other types of groups, and that prevents the reacting partner from approaching it. Okay, so now let's talk about the oxidation step. Okay, so from the alkyl borane, so far we have this. Let's abbreviate this part of the molecule as R. So everything except for those two hydrogens that's attached to the boron, we're going to call R. And what we can recognize in this structure, this alkyl borane, is that it's actually going to react more. It's going to get hydroborated 2 more times because we have 2 more BH bonds that can add across 2 new alkenes. So 2 more hydroborations can occur. And that is because we still have 2 more BH bonds. Okay, so when that happens, you're going to end up with a structure that looks like this. In the oxidation step, remember you're using hydroxide and hydrogen peroxide. So what happens between those two in the background is an acid-base reaction. So the hydroxide accepts a proton from peroxide. So now you get what's called the hydroperoxide ion. And this boron is still sp2 hybridized. It only has 3 bonds, and so it has an empty p orbital. The hydroperoxide ion can attack that. So now you have a structure that looks like this one. The boron, because it now has 4 bonds, has developed a negative charge. What happens at this stage is that one of the alkyl groups is going to get transferred from the boron to the oxygen that the boron is attached to. So the way that we would draw that is to move the R group over with this pair of electrons. And the consequence of that is that a hydroxide ion is going to get pushed out. Now, one of the driving forces for this step to happen is that the oxygen-oxygen bond is very weak, and so it's broken easily. So here you're going to end up with this structure. And then the process just repeats. So another hydroperoxide ion attacks. Another alkyl group migrates. So that happens 2 more times until what you end up with is a structure that looks like this. This is called a borate ester. And in the presence of water, each of these OR groups is going to get protonated and give you an alcohol. And the byproduct here is BOH3, which is boric acid. So that's it for the mechanism of hydroboration oxidation. And again, this gives us an anti-Markovnikov alcohol. So the terms Markovnikov and anti-Markovnikov have to do with the regiochemistry or the regioselectivity of an addition reaction, of particular addition reactions. But what about the stereochemistry? So let's take a look. So for some of these reactions, some of these addition reactions, we do need to consider the stereochemical outcome because it's always the same and it's very predictable. And so we want to be able to predict the products based on what's happening in the reaction. Hydroboration oxidation, which we just saw the mechanism of, is what's known as a syn addition. What this means is that the elements that you're adding across the alkene add to what we call the same face of the alkene. Now, first of all, let's think about the faces of an alkene. So I'm just going to draw an alkene up here. And let's focus on the carbon on the left. So that's an sp2 carbon, and as such, it has a trigonal planar geometry around it. What that means is that that carbon and any atom that's directly attached to it all occupy the same plane. All of those atoms occupy the same plane. Now the carbon on the right, I'm going to highlight that in a different color as well. That's part of that plane, but it too is an sp2 carbon. And so all of the atoms attached to it are in the same plane as it. So what we can see here is that there's really just one plane. So all the atoms that I've highlighted, I'm going to highlight them again now in a new color. Oh, this is making a really big mess. That's clownish. Anyway, all of the highlighted atoms are in the same plane, which means that the alkenes in the vicinity of the double bond are planar. As such, they have what we call 2 faces. So the front face would be the face that we can see from this point of view, looking at the screen. if we were able to go around behind the screen, we would see the back face. So a front face and a back face, or depending on how the alkene is drawn, people might call this a top face and a bottom face. But the point is that there are two faces. So a syn addition. If you're adding the elements of some compound, let's say XY, we'll just keep it general, across an alkene, if this is a syn addition, what that means is that X and Y are attaching to the same face of the alkene. So in the product, they're either both going to be coming forward initially, or they're both going to be coming back. If they both attach to the front face, then they're both coming forward when we draw the product. If they both attach to the back face, then they're both going back as dashes when we draw the product. All right, so let's see how to draw the products of this and how to analyze these results. So we're going to bring in some other ideas that we talked about in stereochemistry. So we're going to start applying stereochemical definitions and ideas to what we're doing here. So we're starting in this first example with this alkene. We're going to treat it first with BH3THF, and then second, we're going to do a hydrogen peroxide in aqueous base step. So we recognize those reagents, and this is very important. You want to be able to see a set of reagents and remember what it is that they do. We recognize that, or those reagents, as being the ones involved in hydroboration oxidation, which is appropriate because we're starting with an alkene, and that's what happens to alkenes in the presence of these reagents, is a hydroboration oxidation. Let's look at the alkene. This alkene, and I'll leave it to you to prove this to yourself, is achiral. As such, it's optically inactive. So our alkene is achiral and optically inactive. Now, if we extend that analysis to BH3THF, we would find that that too is achiral, as is hydrogen peroxide and hydroxide in water. So what we have going on here is optically inactive starting materials. Okay, let's first draw just the constitution of the product. So getting the regiochemistry right, attaching the OH where it's supposed to be and the H where it's supposed to be. So let's do that first, and then we'll worry about the stereochemistry. So we know, because we recognize these reagents, that hydroboration oxidation is an anti-Markovnikov hydration, meaning that the OH will attach to the less substituted alkene carbon, and the hydrogen will attach to the more substituted alkene carbon. So the constitution of the product looks like what I just drew. Now let's draw the product, or products, showing stereochemistry. So let's say that the OH and the H attach from the front face. Now looking at the structure of the alkene over on the left, I just highlighted the alkene carbons. They start out as sp2 hybrids, but in the product, they've rehybridized and now they're sp3, which means that they now have tetrahedral geometry around them. So now we have to draw wedges and dashes. So if the H and the OH attach from the front face, then we would draw them both coming forward. But then the groups that are also attached to those carbons are going to get pushed back. So let me put in those details in my original structure so we can see where all that stuff comes from. So this would be the result if the H and the OH attached to the front face of the alkene. And now let's draw the result where they attach to the back face. So we'll draw them both. We'll draw the bonds to both of them with dashed lines to indicate that they're going back. And the consequence of this is going to be to push forward the methyl group and to push forward this hydrogen. So this would be the result if the H and the OH attached to the back face. Now let's redraw these without the hydrogens, the extra hydrogens, so that the structures are a little bit easier to analyze. Okay, so those are our two products. These are redrawn without the H's. Okay, now, when you compare the two products to one another, what you notice is that they have the same connectivity, the spatial arrangement is different, and so when you push on this a little bit more, what you're going to find is that these are enantiomers. Okay, now, the next question, though, in this reaction is, how much of each of these enantiomers do we get? For us to get more of one than the other, there would have to be something different about the two faces of the alkene. Now, typically what this means, you can think of it this way, is that there might be something present on one face that's blocking that face that's not present on the other face. So the face that has something maybe in the way of where the reagent wants to get in, that face is going to be approached more slowly. And so product that derives from an attack on that face, you're not going to get as much of it as you will from the attack that's easier on the other face. Now, in the case of this alkene, the faces are actually pretty much the same. So the reagent is going to approach one face at the same likelihood, let's say, as it would the other face, meaning that the rates of approach to either face by the reagent BH3 are going to be the same, which means that you get the same amount of each of these products. So if we get the same amount of each of these products, then we have a 50-50 mix of enantiomers, which you know is a racemic mixture. And a racemic mixture is optically inactive. Okay, so now let's go back to what we did in the very beginning. We assessed our starting materials and found that they were optically inactive. And when we looked at the product, we find that it too is optically inactive. So optically inactive starting materials are going to give us optically inactive product. Okay, let's do another example of this. Okay, alkene. Now in this case, I mixed it up a little bit and I'm using this compound, SiA2BH. This is called dicyamal borane. And this is another boron reagent that you could use to do a hydroboration. You can use this instead of BH3. The second step is exactly the same. Hydrogen peroxide, hydroxide, and water. Okay, let's assess again. Now, sometimes what you might want to do is draw in your H's, like so. So draw in missing H's, we're going to need that a little bit later. What we find when we assess these starting materials, though, is that once again, all of them are achiral, and thus all are optically inactive. So once again, just like the previous example, our starting materials are optically inactive. Okay, now let me draw the structure of dicyamal borane for you so that you have that. So that's that guy. Okay. In our first example, we had a ring, so it was really easy to draw the stereochemistry. We just kept all the bonds in the ring in the same plane, and we varied the wedge and dash notation of the groups that were attached to the ring. If we have an acyclic compound, like the one we have here, we can still predict the products. So let me redraw this and show you the way that I like to do this. Okay, so first of all, let's draw the constitution of the product. So remember that it's a hydroboration oxidation, which means that the hydrogen attaches to the more substituted alkene carbon and the OH group attaches to the less substituted alkene carbon. So the constitution of the product looks like this. But if we want to draw stereochemistry that reflects the fact that this is a syn addition, do the following. In the starting material, keep these three bonds in the same plane when you draw your products, or from the starting material, I should say. So we're going to have one product and another product. And so now what we can do is draw the result where the H and the OH added from the front face. So put those bonds forward and then push the other groups, which I'm going to highlight in our original structure. So those would be these two methyl groups. Push those back. And then in the other product, which I'm going to move over a little bit. Okay, once again, let's keep these bonds in the plane in both structures. That's going to ensure consistency when we draw the products. So in this product, the H and the OH attached from the back face. And that's going to push those methyl groups forward. Okay, when we assess these two products, we find again that they are enantiomers. And again, with this alkene that we started with, there's no preference for the reagent, in this case the dicyamylborane. There's no preference for that to approach from the front face or the back face. There's nothing different about either of those faces, which means that it's going to approach each face with equal likelihood. So once again, we get a 50-50 mixture of enantiomers, which, as you know, is a racemic mixture. And so we have the same thing that we did in the first example. We have an optically inactive product because we started with optically inactive starting materials. Let's do one more example of this, and then let's summarize what we've been doing. Okay, this alkene is a little bit different than the ones that we've been looking at so far. And the reason for that is because this one actually is chiral, and thus it's optically active. So we're using BH3THF again, hydrogen peroxide, and aqueous base. Those are achiral reagents, but that's okay, it doesn't matter. What's important is that there's chirality somewhere in the reaction mixture. That's going to dictate the relative amounts of the products that we get. Okay, when we draw the products for this, I'm just going to go to the bottom line of drawing the products. We're going to get 2. Based on the H and the OH attaching from the front face, and again, I'm just going to show the final result. Remember, there's an H on there too, but we don't have to draw all the H's. So I'm going to leave it to you to take the individual steps like we did in the first example, showing the H initially and then redrawing the product. So that's the step I'm at here. So we get this one, where the H and the OH attached at the front face of the alkene, and this one, where they attached from the back face. When we compare these two structures, what we see is that these are diastereomers. Now, if we look at the starting material, the alkene, I made this one a ring so that it would be easier to see, but it's going to be true for any chiral alkene. In this case, the faces are not the same. So the reagent is going to be more likely, and it's going to be better able to approach one face of the alkene than it is the other. Now, one way that you might think about this, particularly because this involves a ring, is that the isopropyl group, which is pointing back from our point of view, that might block that back face, again, from our point of view. And so it might be more likely that the BH3 would approach from the front face. So that's a reasonable estimation. Now, we're not going to need to know which product, front face or back face approach, which product we form more of. We can make an educated guess like we just did, but that's not really important. What's really important is to recognize the fact that because the alkene is chiral, the faces are not equivalent and we're going to get more of one product than the other. So in the case of diastereomers, when we form diastereomers in these addition reactions, we're forming them in unequal amounts. Now, any mixture of diastereomers that would form from a reaction like this one will be optically active. Okay, so let me restate that for clarity. The diastereomers formed as the result of an addition reaction are going to be formed in unequal amounts, and such a mixture of diastereomers will be optically active. So we started with optical activity in the starting material, and we get an optically active product. Okay, now let's summarize what we did. So let's draw some conclusions here. For these addition reactions, optically inactive starting materials and we saw a couple of examples of this, yield optically inactive product. Now, what we saw in the examples that I showed you were racemic mixtures. So an optically inactive product could be a racemic mixture like we saw. But there's other types of optically inactive chemical species. So it could be an achiral molecule, a single achiral molecule. Or a meso compound. All of those are optically inactive. So all of those are possible products that we could get from these addition reactions. Now, by contrast, optically active starting materials are going to give us optically active product. Now, what is that going to look like? Okay, what we saw in the previous example was a mixture of diastereomers. So that's one possibility. Another possibility, a single chiral molecule. And a third possibility, which we won't be seeing at this level, would be enantiomers, but formed in unequal amounts. Okay, so the one that you would focus on, though, would be the mixture of diastereomers. That's the most likely result that you'll see. So for the addition reactions, because we're going to see some more of this as we go forward, I'd like you to remember that when you form a racemic mixture, it's because those enantiomers are forming at equal rates. This has to be the case, because if they were forming at unequal rates, you'd get more of one than you get of the other one. And then the other possibility that we saw, when you form an unequal mixture of diastereomers, those diastereomers are forming at unequal rates. So the two diastereomers are forming at unequal rates. One is forming faster than the other. That's why you get more of one than the other. And again, that has to do with optical activity in the starting materials. Now, the optical activity or lack of optical activity, when we assessed that, can show up. So optical activity can show up either in the alkene, the organic compound that you're trying to convert to something else, or in the reagents. Most of the time for what we're doing, you're going to be looking at the organic starting material. Most of the reagents are going to be achiral. But just to give you a heads up that the chirality or the optical activity can appear anywhere in your starting materials. It doesn't have to be the organic compound itself, and it's going to have the same result.